Hi everybody, today I want to cover an example that I didn't get to quite cover in detail today. I didn't get quite to finish it. And it was the problem of minimizing the amount of border that I need to bound a rectangle of a given area. For intuition, I want you to think of a similar example, which is that of a rectangle where you want to minimize uh, the amount of perimeter needed to bound a rectangle of a given area. This border here is just like a perimeter that I'm minimizing. Here, it's the square that's going to be the most efficient in getting the most amount of area packed in. And over here, similarly, it's the something that looks like a square is going something that's kind of like a square is going to be the shape that's going to be the most efficient in taking up the least amount of border to bound a given area. The particulars of my example is that this side length is 6. This side length over here is 4. And the constant area, the area that is fixed, this internal area, I'll call this x, is fixed at a given number, 384. And we want to minimize the amount of border needed. I'll call the border A for area of the margins. This equals my blue part plus my red part the blue part here is 6 times this length here, 6 times x, and of course that happens twice, top and bottom. And I have this whole side flank here and here. That's going to be equal to 4 times my length here, my height, which is 2 times 6 plus y. And that happens twice as well. This is otherwise known as 12x plus 8y plus 96. Okay. Now let's convert this to a one variable optimization problem. So my constraint tells me that y equals 384 divided by x. So my marginal area equals 12x plus 8y. Y was 384 divided by x. Plus 96. And we are minimizing under the constraint that x must be between 0 and, well, I can make my extremes are that x equals 0 and x is this super wide rectangle, super wide and short rectangle. And again, I want you to think of this example of this rectangle for intuition for my bounds for x. So let's optimize this thing. Let's minimize the amount of border that I need. Okay. So this is the real reason why I did this example today. It's not just another optimization problem. It's an optimization problem over an unbounded domain. X can go from 0 to infinity. This is an unbounded interval. Sure, that sounds scary, but the process is exactly the minimum of A is going to be equal to the minimum of A and the endpoints. Take infinity as an endpoint here. Endpoint. Okay. Let's look at the critical points first. dA by dx is 12 plus minus 3 minus 8 over x squared. That is equals 0. If you solve this thing, you'll get that x squared equals 256. So x equals plus or minus 16. I don't care about get a root because I'm optimizing over this positive domain. When x equals 16, the area equals, so that's one part of this equation. A of 0 equals, well, 0 plus infinity plus 96. Infinity. A of infinity equals infinity plus 0 plus 96, which is also infinity. So the minimum is the minimum of 432 and infinity, which is 432. And this happened at, this was achieved at x equals 16. Y was equal to my internal area divided by 16, which was equal to 24. So yeah, here is the rectangle that optimizes my the amount of border that I need. Not drawn to scale. Thank you. To summarize this problem, this makes sense. This solution makes sense. It passes the smell test because this rectangle, which is the most efficient, looks a little bit like a square. So it matches our intuition that this example is like minimizing the amount of perimeter needed to bound a rectangle of a given area. And we use some techniques from unbounded optimization.